Okay, so hello everyone to our talk about data-driven development for autonomous driving at BMW. First of all, just some words about ourselves. So, my name is Felix. I've been working for BMW for some years already right now. Before joining the project or the area for doing autonomous driving, I've been working in the central IT department as big data architect. And right now, I'm focusing on kind of how can we design a data center that kind of can handle all the data flows that we need to do for autonomous driving. And I'm also proud to be a member of the Munich Data Geeks. People from around Munich might know, but spread the word. It's a foundation that kind of also does meetups in Munich area and data-driven topics. So if you're around, just join us. And today I also got a colleague with me. So.
Hi everybody, my name is Doğukan. So I'm also working with Felix in the project of autonomous driving in BMW. Prior to BMW, I was working on various projects, machine learning related, big data related in various companies. Now, specifically in autonomous driving project, I am focused on my focus is basically data and simulation.
Yeah. So our agenda looks like, well, first of all, we want to tell you a little bit about the background of autonomous driving and why it really requires data. So might not be supernatural to everyone, also maybe not to people working in automotive industry. And then we're going to talk about how we are getting our data and how we're processing it. So getting our data is something special, maybe in the Hadoop universe, because our data is not originally coming from internet or logs or something like that, but it's coming from a car that has a completely different nature. And it's also having something like automotive formats coming with it and different other stuff. That also is something important to know when we are talking about how we're going to process the data, because it's not just small data, it's huge amounts of data, and also we are handling sensor data there. So that's maybe also not very common for the Hadoop universe, and we want to talk about that. After that, we also touch the point how we're going to serve data to our customers and how we ensure data quality. So before I start to tell you how data is really coming from the car into our data center, I want to give at least a little bit touching the topic of what's autonomous driving levels. Maybe some people already know. Let me just shortly introduce you to those things. So there is the level 0 to 5. Nowadays, most of the modern premium cars, they already have a lot of things built in that you call autonomous driving assistance systems. So that can be regarded as level 1. That's something that helps you doing what you need to do as a driver. For example, you can have something like a speed assistance system that will track if there is a car in front of you that it needs to brake at some point of time, or maybe also you have something like lane boundary checks that will tell you as soon as you're gonna leave your lane that you're right now in there. But as soon as we're gonna see that we are getting to the levels 3, 4, and 5 and something like that, the topic will be a lot more difficult to handle, because then we are not just telling a car to accelerate or break down or alarm the driver that he has to do something. The car then really is in control of what is being done with the car, what is being done with the passenger and the surrounding area. And how the autonomous driving function does that, I will cover in the next slide. So here you can see a BMW 5 Series car that was started to be sold to the public area, so was released in 2016. And that car at that time already had 23 sensors built in. So the blue spots in the picture that you can see there are some examples for sensors built in the car and where they might be arranged. And you can also see in this picture the systems that are built on top of that, like speed limit assistance or active cruise control, to just name some of them. So, as I said, this car has 23 sensors. If you compare with what everyone might know, a smartphone. Smartphone has one camera, maybe one front, one in back, microphone, GPS, so that's 4 or 3. This car has 23. And that's kind of a car that has been built a long time ago and is already sold to public. So guess what? The newer cars for the autonomous driving might have even more than that. So to shortly touch the thing like what is data-driven development for autonomous driving. I want to show you this cycle that kind of starts on the left-hand side with test drives from test vehicles. So we are talking about development vehicles, not the customer fleet, not publicly available cars. Those cars are driving around there in the real world, and they generate several terabytes per hour of data coming from all the sensors. Those amounts of data, we're going to need to store that to a data center. We're going to ingest it there. And then there's also this magic number that already has been communicated some time ago by BMW, that our goal is to collect about 500 petabytes per year of data from the cars. So that's a number that already punches us up in the area of those notorious big companies of the internet world that have a huge amount of data. Maybe sooner or later BMW or the other automotive will also be in that area. Maybe, we'll see. So, and from the data center, we of course need to also structurize and find out what's the good data, what's the bad data. We'll have a more deep dive in data quality later on by Dokan. And from the data, of course, we also serve that to our customers. They are building autonomous driving functions, so there might be robotics engineers or different other ones. Also, of course, machine learning, deep learning, very important topic. And those things are also enhanced by simulation that you can see on the right-hand side, the bottom corner, that will also enhance kind of the variety of data that we get from the real world by some simulation data, where you just adjust some of the parameters of the scenario that you saw in the outer world and just get a lot of variation in that will help to kind of have a good data for your machine learning algorithms. And also reprocessing is playing a big role in that area, because law says we need to have several millions of kilometers to apply our function on, and it needs to run safely. And we need to prove that. So we need to, at all the development cycle of our autonomous driving project, need to later on take all the data and apply sensor functions to that. So that's taking real image data and putting it through the function. And we need to prove that kind of the thing that we are selling to a customer later on really works safely. And that's challenging also. And then, of course, there's the part where the developers will kind of deploy their algorithms they built to a real car, will end up in another test drive with a newer function version. And to more data, and that's kind of a whole circle. What we are touching now in the talk today is the upper part of this circle. So we're focusing on getting the data into data center and organizing, structuring, and stuff like that. So, as I already said, 500 petabytes per year. Well, we've got a lot to crunch. How are we going to do that? With squirrels? Oh no, I don't think so. So, here's our data journey overview that we're going to have throughout the talk, some deep dives in some sections of that. From the left-hand side, starting at the car with a logger device, ending up some data in the file getting ingested, and then we start the Hadoop magic on top of the data that we collected in the cars and kind of crunch it, build something like a data lake structure, and later on serve it also to the customers. They build some analytics, machine learning, whatever on top of that. So, first of all, how we get our data. As I already mentioned and showed before, there's cars. Cars have sensors. So we need to somehow record it. And before really showing how we record it, I want to just simply touch a topic like the file format. That's an automotive standard coming from the ASM Foundation that has been built by several OEMs to kind of collect measurement data from cars. And we are using that in a logger device that spits out all this data in this format. This format has a lot of various usage scenarios, and we are using it in one specific way. So we have a logger device. You can see an example on right-hand side uppercase. We are using it very much logger-centric. So our problem really is that the car with all those sensors inside produces such an amount of data that logging that data even gets challenging, because you really need to write it down to a disk, and those car bus systems are not super simple. And logger devices need to really figure out what they receive from the bus systems needs to go to a file as soon as possible, so we are just writing it down FIFO. We are not using a sorted MDF format, what you could also do, but we're using it unsorted. What also you need to take into account is what I wrote down in the lower part about our MDF4 files. We have one contiguous block of storing record payload data. On the right-hand side, you can just see an example that I created myself with one of our software pieces. So you can just see it's binary. You don't really understand much out of that. So to make it a bit more understandable, I wanted to show at that slide how kind of an MDF file could be structured inside, to just give you a short overview about what you're really facing there, because it's not CSV, no JSON and stuff like that. It's something different. So the file itself, it starts with header block, and under that, the header block just tells, okay, I'm an MDF4 file, and under that, you get a lot of MDF blocks. They are building a tree-like structure, so struct of structs, you might know that. And each of those MDF blocks has itself a header that tells what's the block about. It has links to other blocks, building a tree-like structure, and also a data section that contains something like metadata. But to just really mention that, the lot of MDF4 blocks that you will see in the upper structure, they are kind of super small. It's coming down to one data block that's shown on the right-hand side, and this one data block will just have a header telling, okay, I'm data block, and has a huge data section, no more links, because it's a leaf block. And the data section will then store 99.99% of the whole data from the MDF4 file. So what BMW now did is that we already invested kind of a real lot money to build up a data collection fleet that can get us all this data that we need for our users. So we've built 40 vehicles in 2017 based on a BMW 7 Series car, so a car that also can be bought in the public. But the cars are enhanced with newer and even more sensory systems that we are using for autonomous driving. I cannot tell about in detail because it's subject to change, but yeah, you might imagine it's even more data than the previous cars built or got us. And data logging in the car. This picture shall just give you an abstract overview about how this really happens inside the car. So you can imagine the car on the left-hand side. In this example, it's just an example, has one video camera on the front and maybe two short-range radars on the back. And has a logger device inside that is wired with those sensors. And from those sensors, you can see in the middle part of the picture that here those binary streams are kind of coming into the logger. And the logger has kind of a configuration that says, please attach that binary stream to something like a file set, we name it. File set because there are multiple of those files in the logger system on the disk later on. One file set just says, okay, this one kind of source, I want to dump it into this file, then the other goes into another one. Just for some reasons that we are going to process that later on. So Logger also has some configuration that just helps you to find out later on where the file was recorded, in what conditions, and whatever. And as you can also see, the binary streams, they are really going in a FIFO principle down to the MDF4 files that you can see up here. So that's kind of somehow mixed up. As soon as data arrives, the Logger will write it down into the file, and as soon as a file limit that we define as 2 gigabytes in our case, so just best first guess, the file will be rolled over and it will write on in the next file. And what's also important to mention here is to just give you an idea about how many files we create. One file, 2 gigabytes, contains 5 seconds of recorded data, something like that. So if we're driving around 1 hour, you can calculate yourself how many files that's going to be. Quite a lot. And of course, not just one file set, but we have multiple file sets, and that's just an abstract thing to show here. It's even more complex in the real scenario. So as we've seen those files now, how they are created from the car, how they are now going into the data center, how we are processing that, how we are approaching that. In this slide, I want to show what's going to happen as soon as one complete driving session. We name it driving session as when you start your engine, drive around, so stop your engine. That's a driving session, a complete one. When that got ingested into our Hadoop cluster, then you will have a kind of a bunch of files on the left-hand side that belong to one drive session. And then we're going to take all those files and with a custom implementation of an input format that we're going to talk about in depth in a second, we are going to read all the data from the binary streams of the files into an RDD. And from that RDD, well, we still need to do a lot of things until we are getting to something like a data object, like an image that you can use for something. We still need to defragment the data. Defragmentation in this case is also something that we found is not very natural to Hadoop in that way how we need to do it. But we're also going to talk about that in a second in depth. And after objects have been defragmented from the bus messages, then we can decode it and later on store it again down to Hadoop. So the whole process will be in Spark, in memory. And besides reading the payload data, we also read the header information, merge that, and dump it down to something like a meta store where we use HBase, by the way. So when we started to work on those things, in the first guess, we of course implemented it just straightforward. But when you think about scaling that up to the numbers that I mentioned before, like 500 petabytes per year, you really want to think about what you need to do to make it happen without taking the whole Hadoop cluster, the whole resources that you got for just processing the ingest. And we have some challenges with that. So we have continuous data coming to our cluster. We need to continuously process it. It's a reactive, like batch approach, I would name it. And the challenges coming with that is that we have thousands of files. And the MDF4 file is using a dynamic record length, but that it's not splittable. You cannot implement a splittable implementation for that. So no input format that can use HDFS block splitting. We need to have seeks inside the files to read it. And defragmentation will cause something like a grouping transformation. Grouping is always bad because it causes network shuffle. So what we thought about is, okay, as we have in mind, we want to scale that up to those 500 petabytes per year. We will really want to think about reducing network I/O. So that's a very important topic for us. First of all, I want to dive into the topic how we implemented the input format and what approaches we used for using that. So as I already said before, the MD4 file is just a binary container. We just dump data down there. We don't know what it is, binary stream of something. So you need some software to read from it. And since MDF is a standard, we implemented something that can read the standard. That's called MDF4 Reader in our case. That MDF4 reader can read one file. But now we're talking about Hadoop, so how are we going to do that? Hadoop has those nice things like an input format that you can just implement, and it will provide a key-value pair back. And you can simply plug it into Spark, of course. So what does the Hadoop input format do underneath? Well, it needs to return a key-value pair from whatever it reads underneath. So we plugged in the MD4 reader into the input format. And in our specific case, we also wanted to avoid network shuffling and that stuff. So we choose kind of DFS block size that is the same as our file size, so 2 gigabytes. That will just simply cause that one file is stored to one block. And if you have one file per one block, then where you allocate your code to read from it will be the same place where all the data is stored. So you can just straightforward read it, seeking and everything like that is not a problem anymore. And simply you get the data that you read from the file underneath inside the same executor partition, again in an RDD. So what we created when reading these files is we split the continuous stream of dynamic length binary records into something that we call an MD4 record that will simply contain some metadata that's coming with the record and the payload data. That's still binary, so still not really usable. But now we traversed from having some file that contains something into we having a Spark RDD data frame. And with that, at least we can work in the Hadoop universe. So there are some approaches that we chose, kind of those file sizes, block sizes. That's just the best first guess. Might change in the future. Defragmentation is yet another topic. As I already mentioned before, you need to group something. So everyone might know that in the past we had something like disk fragmentation on your local PC, and sometimes you needed to defragment it. What we mean with defragmentation is that data that is flowing through the car bus system is also fragmented. So what does it mean? Fragment always means that you split it somewhere, but how you split it? The data that we are throwing through the bus could be, for example, an image like you can see in the slide. So how does an image of 2 megabytes size, for example, fit into an Ethernet message? Well, you would not want to have a big Ethernet message. You have something like some IP protocol in the cars also that is used for inter-device communication, that always has something like sender-receiver and all that stuff. And inside there, we are using a UDP and UDP datagrams, and the datagram then itself will contain a part of the image. So part of the image already means it's splitted. So when we are trying to rebuild it, we need to merge it. And even then, there is more layers of fragmentation happening because the Ethernet IPv4 stack also can have fragments, and you need to also merge them together again. So how that's going to happen? Just shortly, I want to also mention that fragmentation can also spread over several files. So you can also have the case, since image is cut down into small pieces, the image itself might be on one file, the start, and the end on the other file. So as I just said before, we have this collocation of input split being an HDFS block, being one file, being one process. And all that together leads to, okay, I've got a Spark partition, but when I want to defragment in between Spark partitions, of course it would cause shuffling. So that's also something to take care about. And then we also thought about, in the first case, we just implemented it with the reduce by key and group by key things. But we found that this causes a lot more network shuffle as we would want it to have, because we already know from the data, from the nature of the data, that usually you will find from the FIFO principle the most of the data inside the same file. It's just something like 2%, as I mentioned, that is not in the same file. So when we are trying to reduce this network shuffle, first using the reduce by key, group by key, we found we want to apply something different, because our problem is also something different. Reduce by key contains the word reduce, means it's smaller in the output. But our output is the same as the input size, so we are not reducing, really. So defragmentation also requires something like completeness. It's UDP messages, super unreliable, in the protocol, can be sent twice, and all of different stuff can happen on that UDP protocol level already. So it might also be the case that you just don't find every pieces of the images again. So how are you gonna do that with reduce by key? The output might be an incorrect image. That's also not okay. So we found ourselves to just have a very simple process where we just say we do it in a two-step principle. First local, then global. And by that we have an own implementation that backs the whole process, where we have some abstract classes that can be extended and so on for all the different defragmentation principles that we need to apply, because there's a lot of. It's not just one type of images being fragmented, but also other types of data being fragmented on the bus. And from that, we have the process from the left-hand side to the right-hand side. On the top, you can see the description. In the middle of the slides, you will see those boxes that have the same color as the description above. So from left to right side, you can see the RDD number 1. It has data inside that can be merged, because in this example, we just use something like completeness for us means I have 4 fragments, then I can merge it together. And some of the fragments that are contained in the first partition cannot be merged because they are missing something. So what I'm going to do in the RDD number 2, I built that on top of the RDD number 1, just filter for those things that can be completed, and then just merge it to RDD number 3. And the opposite of the filtering, I'm going to apply for the RDD number 4 that's built on RDD number 1, and there I'm going to get all the rest. So all the rest, as I said before, it's just 2% of the data, so very small amount. And that one I can merge simply using whatever, group by key, reduced by key, using some shuffle, because it's just 2% of the data. Later on, I'm putting a union on top of that, and there I am. There I got my defragmented stuff. So kind of, this is the abstract principle. Unfortunately, I don't have the numbers for the group by key, reduced by key function that we had kind of sometime in the last year, where we found to have this other implementation. But that's kind of some numbers where we said, okay, we are reading in one job something like lots of gigabytes in there. And as you can see, the shuffle is less than even those 2%, because we really cut it down to what really needs to be shuffled, and not what reduced by key or group by key would shuffle. So at this point, I'm going to hand over to my colleague Dokkan, who will cover the next steps.
Okay, then. So let me quickly recap our journey. So as you know, our journey starts with the car, all the sensor data being logged in the logger inside of the car as an MDF4 file. And later, once this drive test session is done, this all data inside of the logged logger is being ingested to our data center. And once the data is copied or ingested to our data center, then it's available pretty much for the processing and further operation. And by using our own input format or defragmentation technique in a distributed fashion in a high scalable way. So I will continue with our journey with the serving part. So basically now we have data. It's time to serve this beautiful data. So as you can see, as already know, so our data center based on the Hadoop system. And all the data we processed is saved in HDFS, HBase, or some other storage solution inside of our ecosystem. And basically, as you can see here, there are some image data, some environment-related data, some LiDAR data, radar data, and some bus data we collect from the while driving session. And all of them is clustered, partitioned, based on their types, and so on. And one important thing I would like to mention here, all of them is versioned. Because diversity of the data is really huge, so in order to handle this continuous change, we need to also version the data. And we don't only version the data, we also version, of course, the software and hardware. And this also helps us to tolerate the failure and also analyze during the time how our data is changed. So I would like to continue mention some of the important sensors, especially for autonomous driving, LiDAR, light detection and ranging, or sometimes light imaging detection and ranging. So basically, it's same principle like a radar, but it uses the laser. And it's good for generating like localization, mapping, or obstacle avoidance, and also generating 3D map. So basically, it's just fire millions of the laser beams, and then calculate once these laser beams bounce back, and all the data is used to create the 3D mapping. And there's some disadvantage, of course, other than it's expensive. It's not always reliable in the bad weather conditions. Sometimes, for example, when it's rainy, super rainy, or the snow, the reflectance of the LiDAR might be affected, and then this might produce poor data. Next is radar. So there are two types of the radar in the car. One is far range, other one is short range. So basically, the radar is mainly used for moving object detection, and data is calculated from the radar can be used to measure the velocity of the moving objects and so on. And basically, so for far-range radar, usually used for the sensing long-distance object, and short-range radar usually used for the collision avoidance, emergency brake, and so on. And advantage of course, the comparing the LiDAR is more reliable in the bad weather conditions. So next, of course, the images. So depends on the autonomous driving car level. It might be 8 camera or even more. And the camera or the images being usually used for the object recognition, like pedestrian detection, traffic light detection, this sort of detection task. And as I said, I mean, this depends on the level of autonomy. It might be 8 or more. And considering the usual RGB image or the grayscale image, in autonomous driving context, we have the RCCC image. 1 red channel and 3 clear channel. And this specifically or the good for the building the self-driving cars. That's why also there's a red channel to capture the important traffic sign. And basically, also when this test drive is run, main data is being generated this image. This really huge amount of the image being come. So that's why also sometimes it's compressed or uncompressed. And for the uncompression, so decompression of these images, also we have some decompression algorithm based on the lossless compression. And in our Scala, our own, because we also want to handle the decompression in a distributed way. Unfortunately, in the GVM landscape, there's not really huge support for the computer vision. That's also one of the reasons we have our decompression. Another important thing is, so RCC image is good for the autonomous driving, for the machines, but visually it might be not that good. So we have also some filter, again, implemented in Scala actually, in order to make this RCC image visually better. So those were the three basically main or the important sensor for the self-driving car, but they are not the only one. So basically, we have like lots of sensor data, and all of them is important, and ideally, you want to bring all of them together. So now we get to know the bit data, and this data, of course, create a huge interest. So let's get familiar with our users. So who are our users? So basically, overall, we have different data types, and this also like diversity of the data also create really diverse user profiles. And all of them, of course, sharing the same goal, building the self-driving cars, but basically, they have different background. Some of them might be really expert in C++, embedded system, but some of them might be not really having any experience in the big data landscape. And of course, their requests also different. So some of them, for example, machine learning engineer here, he might be interested or she might be interested in driving the highway in a rainy day in Parquet or ORC format. On the other hand, some software engineer might be interested in JPEG data. So remember, we have the RCCC, and this means we need to convert the RCCC, perhaps some decompression, some applying filter, and encode as a JPEG. So for example, or robotics engineer, he might be interested in some IMU or the GPS sensor data. These two sensor data is mainly used for the localization. GPS is good in accuracy perspective, but it's not that frequent. And IMU is not that good, but it's frequent. So ideally, you combine these both of them, and then, of course, there's going to be error. This accumulated error then later filtered out some technique like a Kalman filter. And this robotics engineer interested in this file format, ROSBAC, is basically a container for the ROS, and ROS is the robot operating system. It's also another system being used, especially in the developing self-driving car landscape. Other example, HDF5. This is the hierarchical data format, also not Hadoop-related file format. This is also being widely used, especially in the research area, or some other important, as many of you already know, data frame or data set in Spark. So now pretty much we have data, user, everything, so we can also build the solution type of it. So if you think about here, so we have the data, we have the knowledge. I mean, then basically what we do, the different areas. So we do some machine learning, deep learning, we do some sensor validation, we do some development in the ROS. And idea is basically, I just want to emphasize, this autonomous driving technology is not a single technology. Rather, it's complex and have subsystem. And if you think about really high-level abstraction of this solution, basically there are three main components. One of them is the sensing and perception, basically understanding of the surrounding of the car. Other one is the localization of mapping, so localize the car in certain given time. And other one is the driving strategy. So like when the autonomous driving car want to enter the roundabout, you need to negotiate with other cars or perhaps lane changing. So these all solutions actually show us you need to combine multiple sensors, fuse them in order to increase the reliability and safety. I mean, this all solution, all data, all user profiles, of course, you need to come up with certain approaches. So our philosophy, in order to build these self-driving cars, is enable to users. So as you can see previously, there's variety of the user, and they are interested in very different data formats. So what we don't want also they just go and decode data, they fragment all the things they need to do from scratch. No, we want to enable them so they can use the data we collect and they can build their solution on top of it. Also, we don't want to build everything for them, so like the different file format might be relatively scaled. And as I mentioned, some of them is not that experienced with the big data, so this means sometimes we do some Spark trainings internally, we do some onboarding for the new customers, and overall is the idea, this abstract away this complexity in a balanced way, so we can work all together in order to develop the self-driving cars. But of course, it always comes to challenges. Big data comes with the big challenges. So this big data, it requires a sort of like indexing in order to access this big data. So we need to have to also build some scalable way to access this data in a fast fashion. Another thing, as I mentioned, the variety of the data continuously changing. It requires really versioning, and not only software, hardware, and the data itself. And also, as I mentioned, each user requires different data. This also means we need to enable them to so they build their own solution. And last but not least, we also have multiple data centers across the globe. Many times it's very problematic to ship the data. It's also not wanted. So what we want, actually, we want to move the knowledge or the algorithms so we can build the self-driving cars, not for only one location, for the whole system. At the end, I mean, very simply, what we want, we have this all partitioned cluster of data, and we have very nice search grammar. So user goes there, selects some snippet, some camera images, some rainy day, and gets some RDD. And then up to user build something top of it. And I just want to emphasize, so sometimes users are not interested in the whole data, small pieces of the data, small snippet. So this means we also need to go to each data, find out this interval or something like this, and then combine them and then give the data. This is also highly challenging. Okay then, let me continue the last section, data quality. So data quality itself is very important, but it's also very important especially for autonomous driving. So I'm going to start some motivation, some examples, and then I also give some more technical details about our solution for the data quality. So let's get started. Okay, remember, we have this test vehicle. It's drive around after 1 hour, and then we just realize actually all the data is waste. So, I mean, we just waste all our resources, all time, and we don't want to do this. It's really redundant operation. On the other hand, so somehow, let's say we ingest the data, but we cannot use it for some reason. I mean, we have really huge amount of data. We cannot scale this amount of data with our data center, so we don't need this unwanted data. This is also not desired situation. Another things, so we might have not error at all data is valid, but might be not interesting for anybody. So there's no sense to keep this data to here. It will just create a problem. We will not gain anything. And at the end, when it comes to, it's all about the good, bad, and ugly data. And remember, we have this beautiful LiDAR data. When this comes to our system, we are happy. It's interesting. But it might be happen, sometimes some data might be missed. So remember this MDF4 file being collected, when they ingest it, some of them is missing. So they are totally fine, but still they are not completed. Or worst case, we might have thought, okay, we have all the data, but at the end, all corrupted. None of them can be used. So what we want, high quality data, not only for the like valid, and in terms of the error, we also want the interesting data. At the end, it's not only about the quantity, it's also all about the quality. So, but we are living in the real world, so everything is not perfect. So there might be some errors. So some of them is related to while we are driving. So the logger, which logs all the data collected from the sensor, might be some issues. One camera might be, for some reason, might be dropped some images. Calibration error, for example, I mentioned the LiDAR. LiDAR itself is really relies on its calibration. And calibration, actually, this optimization process, which requires many parameters. And if some of them is corrupted or missing, then we cannot calibrate the LiDAR data, and then this means we cannot use it at all. And some sensor even might be somehow broken or not giving any information to us. But still, as I mentioned, so this is not enough. We might have perfectly valid data, but we are not interested in the data which is not driven even like in the highway or urban. We want the data we want to drive which is driven in the rainy day at the night. Or we want our car drives in the crossroads with multiple traffic light stops. We are really interested in this sort of data. Sometimes we have data is in the car, stay in the parking lot 1 hour. So it's not interesting at all. So we really check the kilometer driven to our car so we can get inside and we say, okay, this is the data we want. So how we handle this data? This basically challenges. So we have the centralized data quality framework built with the Spark, and we use the Kafka for inter-application communication. And there are some techniques we use here I want to mention. So basically, just for the clarification, it is not a streaming application, but we use the Spark streaming scheduler in order to schedule our job, some of our part. So then it will be reactive. So basically, we have our custom input the stream, and think about the Spark streaming is a micro batch. There's a batch duration. It's triggered and create RDD. And we use this scheduling, and whenever this triggered, our custom input the stream goes like checking the mailbox if there's something for him. And if it goes and create the RDD. An idea overall in the data quality framework, so we don't want to, like for the checking if the data is good or bad, to just go check everything. We just want to get the quick insight, and we call this like indicators. And then on top of these indicators, we make decision. We create a metrics. And here you can see overall architecture. And if you put this in the whole cycle, it triggers whenever data comes. Whenever data comes, we create these indicators, as I mentioned. These are the like sort of insight data comes. We don't do the defragmentation yet or the decoding. And then we send the message to the Kafka. We say, hey, there's a new data arrived. I did some quick check, and these are it's saved in the HDFS. And other module goes the Kafka, check, hey, oh, there's a message for me, and see where's the data, and then goes to these places, and then create the metrics or the reports. Then actually this helps us to build automated data retention policy. Then we don't have to keep the old data forever here. Back to our journey. Remember, we start with the car, we process the data, and then we did some serving, we did some machine learning type of it, we built our application, and we gained some knowledge, we built some algorithms, and then now we go back again the car, and then we gain another step in the building the fully autonomous driving solution. And saying that, so basically, we are also, and comes the end of the journey. Basically, the journey is exciting. So there are still lots of tasks need to be done. So we are not there yet. But basically, on the road of autonomous driving, I would like to say, there's industry still in the early stages. And BMW is one of the pioneers, and we are making the solid and the safe steps in order to build this self-driving, full autonomous driving solution. And we have already established the autonomous driving campus just outside of Munich to build the next mobility. And as you know now, we have the data. We'll be also in Strata, London. And if you have any other question or anything you want to learn about us, please visit us in the booth. And that brings us to the end. Thank you very much for your attention and interest.